Hello, well then, welcome to Decode or Not to Code. I'm Mele Eva, and as always, I'm very happy to be here today. And I'm joined by Stefan. How are you doing?
I am doing great, although it's the 1st of April. I never usually do anything 1st of April's day, but last season we had an idea, and I'm glad we are now committing to it.
Yeah. Did you get tricked already today by anyone?
Well, I haven't, but I got glad that I wasn't because I started a new job. That would be hilarious.
That would be intense. Quite brave to start on the 1st of April, to be honest. Hi, Eric. Thanks so much for joining. If you're new to the show, the two of us meet every other week and do some coding. Stefan is actually quite the genius when it comes to .NET, and I'm usually just trying to keep up. But we continue to learn from each other and with each other, and from and with you, our viewers. We had a really fantastic episode last time as well, where we were joined by Conrad, Kevin, and Christoph, who are the authors of the second edition of Pro.NET Memory Management, and we'll continue on this theme today. We will not manage memory. We will play around and trick the memory, or play tricks with .NET memory. We'll show you what happens if you haven't read their book and don't know what's going on under the hood. You could run into some problems, and you could have done that before this episode, but once you've watched it, you'll know all about it, and also how to avoid funny business in your code. But before we jump into all of this, please take a second to follow us on any of your preferred social medias. We have a list of all the ones. Yes, there it is, that we have. Just give us a follow, just because we've announced it a couple of episodes ago, but we will be taking a short break, just a couple of weeks, just in preparation for the conferences that we're going to be at. We're going to have some talks at the NDC Oslo and also at Techorama. So come join us at the at the conferences. Unfortunately, it means that we'll have to kind of take a step back from streaming, but just for a little while. But however, you do not yet have a date for our next stream, so it's very vital that you follow us in order to stay up to date. If you don't want to miss, I'll come back. But yeah, it should be about 2 months, something like that. We'll see.
So yeah, I guess June-ish.
Two-ish?
June-ish.
Tune-ish?
June-ish!
June. Oh, yes. My God. Sorry, I didn't hear you.
No worries.
Okay, June-ish. I get it. All right. I guess that's it. I think we're ready to jump right in. What's the first shenanigan we're going to have a look at?
Yes, indeed. Actually, the connection to a previous season where we first did involuntarily a bit of a shenanigan. We said, hey, this will kind of make a perfect 1st of April Fool's episode, and then we gathered ideas. We built up a bit of a backlog, which not only is resulting, which not only has resulted in a talk, Breaking Bad with C#, but also is connecting, as you said, to the book Pro.NET Memory Management. We're gonna do some unexpected things and unsafe things to explain how stuff works under the hood. Just before we run this example, I'm super happy that Michael made it. Thank you very much for joining. And our Waslin expert, Jason Bock, is also here.
No way! Welcome, Jason. Thanks so much for joining. Wow.
Time for some shenanigans. So we built here our class, and our class is implementing the I-equatable interface, and with that also the equality operators. And well, when we have, let's see what the code does. If we have create a new instance of this, let's pass in. Oh no, 41, that's invalid. 14. We check if the instance is not null, because Well, if the instance is null, what we learned in our null episodes in the previous season, that we get here a warning that we may dereference possible null reference. Well, and then will cause a null reference exception here. So we should check if it's not null, so that we only run this code and dereference this when we are sure that it's not null, because we actually annotated it as maybe null. And when we run this, we should get this toString executed, but that's not quite happening. Well, let's try the opposite. What if we set it to null? We don't get any warning, so this null check should be fine. We should definitely not call this code. But we do get this nasty null reference exception that we caused.
What happened?
Involuntarily last season.
Did you play a trick on me? Yes, you did, didn't you?
Can you imagine where the evildoer? Ooh, well, Jason already has figured it out way too quickly.
He's way ahead of us.
Yes, indeed. We played some shenanigans with operators. And yeah, in our equality operator, we implemented equality here incorrectly. And we actually do a not null check here. So this null check is kind of now inverted, and we actually do run now in this code. Now the compiler doesn't do any dynamic analysis of how we implement all the operators, but the compiler assumes that we implement the equality operator, but also the equals method, everything that is related to equality correctly. Therefore says, we check it for null, everything is cool. Now, although we played some shenanigans, so our equality operators are nothing to apologize. Quite the opposite. Glad. It's amazing. Can you remember how we could fix this? Because maybe our class, maybe that's not our type. Maybe we don't have the source for it. Do you know how we could still do a null check without calling this nasty operator here?
We could use pattern matching. Is that what it's called?
Would you like giving that a try?
Yes. So instead of this, we could try is not null. Ooh, get a warning.
Yeah, well, we do get a warning because the compiler figures out that we set it to null and then do a null check doesn't make sense, really. So this is never called. But yeah, now we don't. Now, indeed, we do a pure null check. Do you know how we could write this? Oops, excuse me. Oh, I cannot undo your code. Cool. Do you know how we could?
Yes, nice.
Do you know how we could write this differently to still have the not equals operator, but still not go in our invalid bad operator?
Well, I guess we'd have to implement our operators correctly, or we could use a record clause, right? Isn't that? Does that implement this for us?
Yes.
Doesn't that do the work for us?
Indeed, we could implement a record class here and then get rid of basically all of the equals and all of the get hash codes and the toString, because that's all implemented for us if we turn this into a record indeed. But what if this isn't our class?
Oh, yes. You said
we don't own it. We can't change it.
You can't change it. No, what would I do?
What we could do is take a look what the compiler does if we apply this pattern. So let us build this. Let's go to, let's see what this code decompiled looks like. And I'm actually surprised that it looks like this. Kind of should look differently. I was expecting, I wasn't expecting our class here to be used, because if the compile time type is, wait a minute. Oh, sorry, no, I'm not sure. I was expecting something else. Maybe let's head over to Sharplab, because
Yeah.
There it is.
Trusty sharp lib.
.io. This is where not sure what I'm doing now wrong here. In wider, if we have, let's copy our class over. Put the using here. Okay. And if we now have, let's say, our class here, and we could say return is not null. And take a look at it. Now what the compiler does is for this null, for the static null pattern matching, it upcasts this R, or this instance of our class, to the static type of object, and then we use the operator of object. So if we actually now go into our code, we see when we use the equality operators, we see that actually is green, and this is on our type. Now with operators, there is no inheritance. You can overload an operator, but they are not the runtime type is not evaluated. So if we now cast this to object,
nice.
Now we see that this is no longer green, and now we actually get the equality operators of object, and they do reference equality. There is none of our code is invoked, and well, before there was pattern matching, this is how you would do a pure null check. And also, if we would take a look at the IL code, we would then maybe let's do this in Rider, because Rider shows this quite nice. We can click it. If we go to the IL code, we should only see that we load this instance and a null and just compare these against each other. And there we have it. We load an argument, we load null, check if they are not equal. I think, not entirely certain. Is this they are unequal? Compares two unsigned or unordered values. Yeah, so checking this against the null reference. But if we don't do the downcast, the upcast, and actually have our operator invoked, we see that we are doing more than just a null check. We're actually calling, we call our inequality operator.
Yep.
This is now invoking our user or the code of type, and it's first of all doing a little bit more than a null check. And also, if the null check is implemented wrong, then we get the errors. Well, a type better implement the null checks, right? But you could say if you want to have a pure plain null check, you could use with modern newer versions of this language, use is and is not null for the pure raw null check.
Nice.
And this is how the idea of the stream started. So let's see what we could do wrong when we talk about memory.
Memory management.
Your salty devil has arrived.
Hello, welcome.
We prepared a tiny demo where we, well, let's hide this. Well, if we just run this demo, we print hello world.
Okay. Yeah. Let's see if that works. Fair enough. That's pretty expected behavior so far. So good.
Yes, indeed. Now I run some code, whatever that does. Still just doing hello world. We have here the hello world literal. We don't do any shenanigans by, for example, changing the console.out to a different output stream or anything. There is nothing of that.
Yeah.
We just run whatever's happening here.
Something.
And now we get April Fools.
What? How? Because we don't pass the string, right? And it's also, there's nothing, it's just console write line hello world.
It is actually when we go in here and would evaluate hello world. I'm now evaluating Oh, no, wait a minute. That actually, maybe Winer does something different. Okay, not sure. I was kind of also expecting April Fool's now, but yeah, it says April Fool's here. We will jump right into how one could, because strings are meant to be mutable.
Yeah.
How we could mutate these and also then do some memory related shenanigans. Just before, Jason is asking if Writer suggests to use pattern matching for null checks. I don't think it does. Let's see. It suggests to use the pattern. Oh, so no, actually, let's see if we have the operator. The operator is overloaded. Let's see if it does. It allows me to negate, to flip, and to replace, but no, it doesn't. Actually, fun fact, I built some time ago code refactoring for that. Or was it a fixer? If we integrate this package, I'm wondering if the April Fool's demo is showing something. Yeah. So actually, in this analyzer project, some time ago, I built a diagnostic that gives you a warning. Well, I guess warning is a bit too harsh. Maybe I should change this to info per default, but gives you a warning if a null check is performed, but for example, the equality operators are overloaded. Then we could change this to a constant null pattern, for example. And I think, if I remember correctly, it's been a while. This also works if we do a null check like via the equals null. I think then also says that this equals is actually overridden. No, wait a minute, it's not overridden, that's overloaded, because we overload the equality and also implement the iEquality interface. And we could also check this to the constant pattern. And yeah, well, we built it as an analyzer fixer combo, but I guess this could also be a standalone refactoring, because I guess this is not sure if a warning here is really warranted. Yeah.
Oh my goodness, hello, Stuart. There's so many familiar faces here today. Thank you so much for joining. That's awesome.
So let's jump back to the shenanigan. Actually, let's not. I just removed the code here.
Yep.
Let's say we have a string.
Yeah.
Text. And well, we kind of know that strings are immutable. So if we would build our shenanigan method and would pass that string, then this method shouldn't be able to do anything wrong to change this immutable string, technically. Now, shouldn't, but yeah, we shouldn't. Do you have an idea what we could technically do?
I do, but I'm not sure if I can explain it very well. But I know that there's this, because we can cast things, right? We get a string, we can cast it as this as span, I think it's, oops.
Mm-hmm.
Wow, me typing live is awesome. And we can just save this in a variable. What do you call it? What do we call that? Naming?
Span.
And we usually also like to put the type in. How do I do that? There's light bulb.
Can I do Control Dot or Alt Enter and then get the suggestion to use the type explicitly?
Yes. Sorry, what was the shortcut?
Control Dot or Alt Enter. If that works via code.
Yes, absolutely. Cool. Yeah. There it is. So, okay. So, but we still read only span of char. So it's read only. So we can't, again, like it should, everything's safe, everything's fine. But
if
the thing
let's give it a try to try to mutate that, and let's just change it to some character. No, we can't, because the indexer of read-only span actually returns a Wait a minute, where is it? Where's the indexer? There it is. Well, it does return, in this case, this character by ref. So we actually, well, since a character is a value type, but since we return it by ref, we don't get a copy of this character, but we get actually a reference, not quite a pointer, but a managed reference to this pointer. But this ref, it's a ref read only. That means we can't assign to it, so we can't change it.
Okay, so we still cannot change stuff. That's okay. But we can. You already mentioned, I guess, the keyword here. We can get a hold of that reference, and maybe we can play around with that. I cannot go to the. Okay.
We need a semicolon. I think that should work.
Oh, okay, perfect. And there's this. So we want to wait. Ooh. Oh my goodness! It's actually already. Can you see my suggestions?
No,
but
let's see. What does it suggest? Oh, right. Yeah, I guess because it sees our actual shenanigan down there, I suppose.
No, does it? Oh, does it? Oh no! Oh, sorry.
No, that's cool.
That's
cool. That's
okay.
cool. That's cool. I really like that because that is one part. That is one part. A span, the read-only span, and the span. Well, that's a view into contiguous memory. Now, our string here, that's contiguous memory. So in memory, the E comes after the H, and the exclamation mark comes after the D. This is one contiguous block of memory. And when we get it as a span, we get a reference to the first character. And also, do you know the second component that we get with a span?
The length?
The length of it, exactly. Which is this, what's that, 12 characters? 13? And because it's contiguous memory, we now have a view over this entire string.
All right, but if we have a view, can we also change that?
We could, yes. Yeah. Well, with a view, what you can do, or with that span, you can slice into it.
Okay.
So you could narrow this view. So what we could do, maybe we start at the L and give it a length of 3, and then we only have LLO. Okay. But still viewing into the same memory. It's not a new string LLO. It's still the same string in memory, but our view is now narrowed. So that's like, this is where span is really powerful, where you can create, allocation-less or heap allocation-less views into your memory. Because if we were doing a substring, we would get a new string allocated on the heap, which then later on may cause additional garbage collections to occur if the application runs for a long time. So that's one thing that we can do with a view. With a span. But yeah, so the indexer we saw is read-only ref. If we had a non-read-only span of char, I call this span ROS for read-only span, and this one just span. If this was possible, which it isn't, because it's kind of valid in the contract, if we implicitly cast or explicitly cast something from read-only to not read-only, we could now freely mutate this, whatever this span is viewing into, because the indexer of this now returns a ref, but not a ref read-only. So we could actually now mutate this. This memory.
We just said that a span is just a reference to like a beginning and a length, and you just wrote a new span there. Can we just reuse that reference and the length, and wouldn't that write to the same place then?
Do you mean because what this memory marshal get reference returns, it doesn't return a ref read only, it just returns ref. So we could get rid of this read only here.
Easy.
And could now start assigning stuff to it. Let's say the A of April Fools, And now we should get, instead of hello world, we should now get
hello world.
Yeah.
Yes, so we do.
And
And
we
we
indeed.
do.
But how can we now get to the next character?
So we kind of need to make this indexing work, right?
Mm-hmm. Okay. Because basically what we now want to do, we have more or less a pointer to here.
Yeah.
You know how this thing is called? How to get, to the pointer to the next element of this contiguous memory?
Yes. Something pointer arithmetic. No?
We could do pointer arithmetics. Indeed.
Yes.
So we'll come back to that. we could go unsafe. Because when we have unsafe code, well, we could have an unsafe block. We could make the entire method unsafe, which now makes, basically this block now unsafe. We did in the project set up, where is it? Allow unsafe code blocks. Otherwise, you can't use the unsafe keyword. And now we could have pointers. So we could get a char pointer to the beginning of this text. But I apparently used the wrong. What am I doing wrong?
To the beginning of this text.
Wait a minute. What am I doing wrong? I need to go cheating. I forgot how to do this properly with pointers. How can we get a...
Oh no.
Again. I'm not surprised. Can I convert source type string to target type char pointer? That's embarrassing. No, this should not make any difference. Shouldn't it? Oh, is it actually? I believe we... Yes. And Knusper knows. We need to... I think this is enabled via get pinup. If I remember this, there is a language pattern for that. We need to use the fixed key. We need to use a fixed statement. And I think, I'm not entirely certain, but basically what this fixed keyword is enabled by is in the string this get pinnable reference.
Mm-hmm.
I think this is what the fixed keyword enables. And so we can now cast this to a char pointer. Thank you very much, Knusper, for your help. And well, now with a pointer, we could do pointer arithmetics. Well, of course, we could now, if we dereference that pointer, we can now again assign like an A to it. But we could now also apply pointer arithmetics. Let's say pointer +1.
Mm-hmm.
And this would be now April's Fool. Let's see if that does work. And now we have, one more. So let's do a couple of copies. Would you mind helping me there to...
Oh my goodness.
Let's just meet in the middle.
I can do the
yes.
arithmetic and you could do the actual...
Fool's exclamation point.
Why are you so much faster than me?
Missing a backtick here. Oh, backwards, not a forward slash. Backslash is to escape characters.
Oh no! What happened?
We went into 2 digits. Cool. Now let's run this. Now we have April Fools.
Yay! Easy. Great.
Yeah, but Jason knows, okay, this is not shenanigans, this is evilness.
Yeah, true.
Because
next level shenanigans.
we kind of could walk over, because the string that we reference here, well, first of all, we need the fixed, because the pointer, this is unmanaged. What we learned last episode is when the garbage collector kicks in, it may do, there is different phase of the garbage collector, and it may do some compacting. Which means when in the compacting phase, maybe we have some memory, we have something allocated here, we have a hole here, then something allocated here again, and maybe another hole and something allocated here. Now we have two smaller blocks free. What we could do is, or what the .NET Garbage Collector does, is just moving then these allocated blocks closer together so that we have the allocations here and now have a bigger block free, or bigger contiguous block free. But when this happens now, the addresses in memory are changing. This is why we have the reference types that we use. Those are not pointers, but managed references. The runtime is taken care of so that all of our references are still always correct. With a pointer, this doesn't happen. So we need to put this in a fixed statement so that during this block, whatever is targeted by this pointer is not moved. So we pin it so that it's not moved around, because this would make our unmanaged pointer invalid.
Oops.
The other thing is, it's just a pointer. There are no bounds. There are no bounds checks. So we could go. We walk off. So that's our pointer is of type char. A char is 2 bytes. So we walk 16 additional bytes over and then mutate 2 bytes to something else. If this is something else in our application, we kind of now have undefined behavior because we're just messing with some bytes in our memory. If we walk too far, we kind of could walk off of the earth. Now we may be accessing some memory that doesn't belong to this process, and then the operating system says, This is actually in best case. When you go unsafe, in best case, you crash. In worst case, you don't crash and then have undefined behavior. So
Right.
that is pure evilness indeed. Can we do this without unsafe code to perhaps be a little bit less evil?
Probably.
I'll bring back your idea with the ref, because the ref doesn't require the unsafe keyword. Let's get rid of this, and now let's bring it back compiling. What we can do is also something like, it's not quite pointer arithmetics, but going in that direction, we could also, since this is just some reference to memory, well, this is now managed reference. So if a compacting phase of the garbage collector occurs, this will be pointing correctly. And also the garbage collector won't clean this up because we have a managed reference to this memory. So it will be kept alive. There is the unsafe type. Yeah, we see whenever we do something with Marshall and something with unsafe, then that's the here be dragon, not here be dragons mode, but the danger zone. You need to know what to do. And what we could do is we add, this is very similar to the pointer arithmetics. We could now add to this first, we pass this by ref, and add 1 to it. And now basically have this. And if we would copy or move this code up here and change it to this shape, we could do it without unsafe code. So how could we quickly do that? Maybe if we format this like so.
Nice.
And then say 1,
Perfect.
2, 3, 4, 10. And 12. I made a mistake, haven't I? Yes, the first is not mutated.
Oh no.
To the A. Let's see if this still works. April Fools. But I guess, this is actually still, well, it's not unsafe. Well, it doesn't use any unsafe C# code, but it's still unsafe.
It has this keyword.
Evil.
Keyword. Unsafe.
Well, that's actually true. I think actually there was a discussion. Was it in the runtime or in the language? If you use the unsafe type, then you would also need to mark. You would need to use the unsafe keyword because technically it kind of is. You're not using any pointers or pointer arithmetics, but still, because we could still just walk over. There were still no bound checks in place. We could still walk over our original memory and now mutate just something in our application. And if this something would be used by something else, we would cause undefined behavior, or we again walk off our memory earth from this process and be killed by the operating system.
Fair enough.
And this is where it would be nice if we could do the span approach.
Yeah, exactly. If we just create like a new span, but like with I guess I teased it before a little bit as well, because this memory marshal also has like what is it called? Create span, easy. And we can put in the reference of first. And then obviously we also need a length. And where do we have the length again? Text length. Okay.
Take this from the length of the text or from the length of the read-only span, yeah.
And I'm gonna try this again. Easy. And now we actually have a completely new separate span, but it does sort of lie in the same place and has the same length. And now we should be able to just fill that span. We're still going to need some sort of index. Do we know? We actually could just, well, we need some sort of...
Wait a minute. Yes, so we do span now here in index 0, and now we basically do the same thing.
Perfect. Oh, yeah, easy. Cool.
And well, now it's that's less evil because now we have, because span is a type, and this type knows the length, and if we go above the length, we would now there is bounce checks in place, so we get an index out of range exception, and we can't go over our world of memory. We go out of bounds. Still,
I could, yeah.
We need to set the length here correctly. If we would go like 2000 here, now we could go above again. So it is
fatal error.
The span itself, it's safe, but if you create a span yourself by passing in some reference and giving it some length, could still be evilness.
But do you know what? Still kind of, because here we sort of like pass in the text, the string text, right? But the truth, like when we first showed the demo, we actually not passing anything. We just made it work with just calling this run function. Do you remember that?
Yes, I do. Well, let's come back to that just in a... No, I'll come back to the comment afterwards. Yes, indeed. Because what if we just want to call this code? Basically, this is what we had was this. We just had the shenanigan method called, and what the shenanigan did is that. Okay, now we need to put the read-only span here. So we have here a string and there a string. They don't look related.
Yeah.
Oh, wait a minute. Index out of range? Oh, yes, of course. Be gone.
Whoops.
They don't look related, but they kind of are.
Because we're not printing. Yeah.
Can you remember why? Because we covered this in our Photo and Memory Management episode. Can you remember?
We did. It's called string interning, if I remember correctly. And it's an optimization that's actually super smart. but also really silly in this case when you play around with it. But yeah, sort of if you have, and I guess it's up to the runtime what is intern and what isn't. But if you have like if the string is like not a variable, if it's just like this, like commas hello world, it's very literal. Yes. It's very likely to be intern. So if you have the same one a bunch of times, it's not going to save the same string a bunch of times. It's just going to save it once and then reference that every single time. Yeah.
You can actually take a look at what are the objects of type system.string in our process, and we will see hello world if we find it. If we find it, there it is. But we'll find it only once. We won't find it anywhere else, although we are kind of declaring it multiple times.
Yeah.
And well, if we start messing with one, we start messing with all of them.
Because
they all point to the same. If I would now step over this code, and did this not work as I intended? Not sure, but we wouldn't have any additional strings. Well, we now did have one additional string allocated because I think what the console write line is doing under the hood. But we won't see a second hello world here. So if we would now want the same thing with the shenanigan enabled, which now basically grabs here the same reference as we would grab here, because they're all interned and point to the same thing in memory. And take a look at our memory now. There wouldn't be any hello world anymore. There would only be April Fools. So we now kind of replace that. If we were to change the string, maybe do one version all lowercase, since strings are case sensitive, this one would not be changed because it's a different string. But we did mess with the one.
Yep.
And I think if I remember correctly, that the intern strings, they are on a heap called the no-gc heap. So they won't be collected. They are interned and then are there. Jason earlier made a comment about if we don't want to do unsafe, we could. Let's see if we can do Control-C enough times to get to our previous version. So if we would say global using first system runtime compiler services.unsafe, because this is where the unsafe type is in. Now we give an alias to first. Now instead of unsafe, we could use fast. That's not. Or we say totally safe. And now, multi-cursor editing. There we go. Yeah, it looks totally safe now.
What could go wrong?
Fast, not first. Oh, did I write first? Oh, I guess I read first. Just meant fast. So we have the fast version of it. Oh, did I not? Ooh, it doesn't. Does it rename it back? If I rename a alias, it renames it back to the original type. So if I rename alias, goes back to the unsafe. Not sure if that's supposed to be. We rename a global alias. It doesn't. Maybe I ask the chat. Just making myself a note. Rename of global alias goes back to, what's the word? Actual name. Not sure if that's intended, but perhaps we found something. And yeah, so we can abuse. Well, not only can we totally break with totally safe code the read-only contract of strings, we could also abuse the internal NES to change all of the strings to something else, which we shouldn't. Never do it. But it shows how spans work under the hood and how with very dedicated set of dangerous APIs, you can do very powerful things, and also how string interning works under the hood.
Yeah.
What shenanigans should we pull next?
Yeah, I'm not sure. We've got a bunch lined up.
Do you have a preference?
Do we? Well, no, I don't have a reference actually. Well, maybe we could go with the tightly packedness. Or not.
That sounds good, because that would mean we can use benchmark.net. Have we used benchmark.net on the stream yet?
No, but we've teased it so many times.
Many times, indeed.
Yes, because we want to do a dedicated episode, and I guess, that might be our next episode, whenever that might be.
Hopefully with...
Stefan has done a lot of reading.
The other book.
He's got another book.
The other yellow book. So let's add benchmark.net. Let's quickly set up a benchmark. We would need to run this. So let's say we have the benchmark runner, because a benchmark.net application is just a console application where we say run, for example, this type. You can also have parse a configuration. You can also parse your command line arguments. You could also have something like a benchmark switcher where you then can select the benchmarks you want to run if you have multiples. But yeah, we keep it easy for now, and we also totally discard the response here. And what we'll do is we also enable a memory diagnoser, so we get some information about memory as well. And what we'll also do is we enable a short run job, because, well, proper benchmark takes a while, and well, it would give us justification or an excuse where we run over time this time.
We never need an excuse or a justification. We just usually do it. But I guess it will also be a little bit, because we're on stream, that would also impact the benchmark. So it's not a very accurate one, anyways, is it?
Yes, you're totally right. So the results will only be for some to see a difference, but the actual difference will be meaningless, because we are not in a great environment right now for benchmarking. And let's say we have a let's do one. I'm not sure naming. Let's do one, or let's do this and that. And let us create a struct. One, which has, should we make, let's not do public fields. Let's be good citizens. Private int value 1. Let's do a long value 2, and let's do another int. And if we would create an instance of this, 1 one. You can also have a setup that's similar to a setup for unit tests. Let's create a new instance of this. And let's call one and other. And let's check equality. Let's see if one equals the other. Perhaps we need that later. And yes, Wider already gives us a hint. It already gives Array a warning here. Something is not ideal here. Now let's go to terminal. Terminal.NET Run. So for benchmarking, we will also run it in release configuration so that optimizations are applied. And we hope that the short job run is being fast, and it is indeed.
Woohoo! That was really fast.
And well, what we get is that we just have two struct values. This quite take, well, it's nanoseconds, but this takes a while. But we also allocate memory here.
Yeah.
That's kind of, so the type that we designed here, that's a shenanigan type. we'll come to the ways of how to fix it just in a bit. But what if I would define a type 2 where I still have an int, and a long, but what I'll do is just shuffle them around. Maybe let's call them also like that. And now let's do the same thing. Let's have one, other one, two, other two. Well, actually, those are structs, so they will be the default values anyway, so we don't really need to initialize them to the default. So we have one, other one, and 2 equals other 2. And yeah, this should be then the type 2. And this returns a Boolean. Now let's see. Would you expect a difference there? It's still kind of the same type, but we changed the order. You're nodding already. What would you expect?
I would expect type 2 to be less allocation and a little bit faster, maybe.
This should finish in just a second, and you would be absolutely right.
Woohoo! Great.
We still have some allocations. We'll come to them as well. We'll fix them too, but we have significantly less.
Yeah.
And we are measurably faster. Well, let's not be focused on how much we're faster, but we can measure in our streaming environment with short job run, there is a difference. What's the difference between those two types?
Yeah, it has to do with the padding and how it's sort of stored on the stack. I'm definitely going to use all of the wrong words and also correct me if I'm wrong, because I already had so many like mishaps today with me just being a little bit unfocused. But not unfocused on purpose, but just because it's been a long day. But like, okay, so let's see what I think is happening. Sort of the thing about structs is, right? When they're stored on the stack, what's being allocated, it's going to sort of look at the largest type, which is the long there. And it's going to at least, we have three fields here. So we're going to have at least, it's going to look at the longest type, and it's going to sort of allocate enough space if we had 3 of the longest fields that we have in this type. So that's 8 bytes. So it would at least allocate 8 times 8 bytes. But then when you actually put those fields into the stack, int doesn't have 8 bytes. It has 4. So there's 4 left. But the next one, long, doesn't fit into that, right?
So just drawing what you explained. So we have
what I
our
was trying to explain.
kind of our 8-byte things, yeah. Then we put in the first integer, value 1 in here with 4 bytes. And yes, and then we have some 4 bytes left.
We only have some 4 bytes left, but the second field long doesn't have 4 bytes. It doesn't fit in there. So we're gonna have to use some padding to fill that up so we can make it to sort of the next little barrier, which is 8 bytes. Yay! So we can put the long in there. Fine. And then we have another int, which is again 4 bytes, which fits.
Yep.
But then obviously we have a bit of space left, so we're gonna pad that up as well. So we actually allocated quite a lot of space on the stack for like much more than we need.
Yeah, we should be. Could be kind of 16, but we actually have 24.
Yeah.
Do you know what the difference here is?
Yeah, well, actually, exactly the same thing happens. We're going to look at the largest type, which is the long. We're going to allocate that like the barriers in like in that sort of in 8-byte steps, and then we're going to have a look at the first field, which is an int, which is 4 bytes. So it fits in the first barrier bit. Yeah, that's great. It's going to fill that up, and then we have the second thing, which is 4 bytes. And it actually fits into the first barrier. So 4 plus 4 is 8. We're going to fill that out properly, and we're going to have no padding at all. Then we're going to go to long, which is 8 bytes. And obviously, it fits perfectly into that second space here. And this is what it's called tightly packed. And that brings with it a lot of goodies. One of them being that you allocate quite a lot less space. But also... And this is where sort of my memory is getting a bit foggy, because it also has another benefit, which is obviously the speed, and that has to do with what goes on under the hood. Can we make that somehow visible?
Yes, let's take a peek under the hood. I just want to check. I'm not sure if I remember correctly how to do this, but actually confirm that we have a 24 and a 16-byte type, so that they are not necessarily just the sum of them. So we have our, there is a size of, and can we say 2 here? I believe we can't because it's not it needs to be an unsafe context. Cool. And if we do the 1 and the 2, let's maybe not run the benchmarks. We should get 24 and 16, and we do indeed. 24 and 16, although both of them have 2 4-byte fields and 1 8-byte field. And here we see the padding or the order has significance because the default, can you remember the default layout? There is something called the struct layout. Do you remember the default? Sequential indeed, which this is the default, which indicates now that the order of how we declare these fields are relevant on how they are laid out in memory, and effectively then how padding is occurring per default. There is also you could also see auto, where the compiler may now order them differently to reduce or even remove padding. And then there is also an explicit, where we could now use the field offset and explicitly dedicate at which, is it bit or byte? But not sure, but exactly where, probably byte, but I'm not entirely certain, but exactly where each field starts, but we need to be very explicit. But yeah, the default is sequential, and therefore order is significant. And also, when we take a look, I mean, where is this equals even coming from? This is not the equals from the base. You're laughing already. Yeah, I missed that message. You smiled. I missed this message.
Welcome to training. Wonderful progress.
In the previous episode, we just saw what was that? What's meal?
Flour.
Also
Just
the
the flower.
Yeah. Yeah, it's getting.
But it's
getting
getting
into form.
better. It's getting into form.
Evolution of the toast. Oh yeah, so this is not, when we hover this, we actually see this is not the equals of object, but of system.value type. So if we were to get the type of any struct, type of, and then get its base type, this will be value type, where the base type of value type now will be the object. So we see it's actually deriving from value type. And if we take a peek at the implementation of system.value type, we will see the equals, how this is implemented. And there is something like this. Can compare bits or use fast get hash code. And if we can, well, we can do this. We can use the fast version if, as you mentioned, our struct is tightly packed. That means there is no padding. Or if there are no GC pointers in that struct. So if we were having a reference type in our struct, we would also get the slower version.
Yeah.
And now we see in the slower version, well, how would you, for example, implement? Because you are now a base type, you don't know which of your types is implementing or is deriving from this value type. How would you implement this? Well, we have reflection where we do exactly what value equality does. We get all of the public and non-public instance fields and just compare each against each from this against each from the other. But we see we use reflection, and that always allocates because these are classes, and then there is an array as well. And this is where those 200 and where's the one? Where these 227 bytes of allocations came from. Can you see where these 64 bytes of allocations are coming from? If we take a peek at the signature.
No.
We do object
From
here.
object? Okay.
What happens when we cast a struct to object? Do you remember how this process is called?
Struct to object?
Yeah.
No, but I should. I definitely will when you say it.
That's boxing.
Damn it.
Ah, yes. So, because this is what we do here when we call when we enable our benchmarks again. When we call the equals, because that's the equals of this value type, and this takes object. So we are now boxing our value type onto the heap and have these allocations. And well, this is where this the recommendation is coming from, that all of structs should implement equality by themselves, because otherwise you may run into trouble of getting this slower algorithm. And yeah, what we do is just comparing all of the instance fields, both public and non-public, against each other. And it's all laid out in code, and there is no reflection. And maybe let's make a type 3. Now I'm using as a base the type 1, which is not tightly packed. So this is still a 24-byte type. So the memory layout is not optimal. When we copy this around, we copy some padding with it as well. But from the equality perspective, if we implement iCreatable of 3 and let writer do the rest, and also implement the equality operators and also get hash code and all of it. Now, if we would run the same thing with 3, we should not only get the faster algorithm, so we should be as fast as the second one, but also have zero allocation. Maybe we give this better names. So this has padding, tightly packed, and this one is equatable. And we do the same thing again. We now have a free, with other free, type free, and would now here say free and other free. And yeah, Wider doesn't warn anymore because yeah, Wider also detects this pattern to warn us if some, oops. Oh, I just hit debug configuration. Benchmark.net complains if we are trying to run the benchmarks not in debug. You can do it, but there is some explicit configuration you need to set to tell it that, yeah, I'm consciously not using all the optimizations in order to debug my benchmarks, because maybe there's a bug in my benchmarks, yeah. Stuart learned that the default layout of structs is sequential.
Yeah, why is that? So if you have auto, you obviously have a lot less padding, right? But does that sort of mess up then your order of fields on the stack, but you still have it? Or why is it not auto per default?
I'm not precisely certain if I remember correctly, but what I think is because of interop. So if I would use this struct between processes, maybe to a C++ to a native process, and I would pass these values between processes, now the layout of the struct is significant because, hey, are my first bytes the integer, or are my first, well, if I have this this example, where is it? There we are. So my first 4 bytes are an integer. Are then the next 8 bytes a value, or is the next 4 bytes a value? And is there padding involved and such? So the layout for interop scenarios is critical. Otherwise, you would interpret in one process the bytes differently than you would in the other process. And I think it's because of that. Now, I'm actually not sure if the runtime is even allowed to, between versions, change the order as well. So maybe if I run it in version 1, I get one order, and then in version 2, it get a different order. I don't know if this is the case, but so I'm not sure if this is also a reason, but fairly certain it's at least for interop.
Fair enough. All right.
And now we should see the best. Yeah. Okay. Well, it's even faster and zero allocation. So not even this. Not only do we have the fast version of it because, well, we just implemented it because we know how we do. We know how to do value equality against our own type, but also we don't get the problems with boxing as well.
Nice.
And Knusper is asking, I thought this is the point of struct layout explicit versus struct layout auto, which is the default. Yeah, no, auto I think allows ordering it differently than declared. And in explicit, you need to declare the start very explicitly. And I think with explicit layout, you could also do something like a union type. If I would have, I'm not entirely sure if this really is a scenario. I never really used it, but this is what's in my mind. What we could do, or what it looks like we could do, is just say, I need to say explicit. We could have a field offset. We could have 2 field offsets of 0, which now means this is an 8-byte struct, but we could interpret the first 8 bytes via this value and all bytes via that value. I'm not sure if this is exactly if I'm explaining this correctly, but I think this is what it's used for union types. Well, the equivalent of a C++ union type. Again, maybe required for interop scenarios. And Jason is seeing an opportunity that there should be an analyzer, not just an IDE feature, but an analyzer that wants during builds for all structs to have equality implemented. No wonder who is going to be first of the two of us.
Yeah.
Goes onto the list. Cool. There is also, when we took a look at system value type, we see there is also well, that's not only this tightly packedness and this GC pointer, and if a struct contains GC pointer, is not only impacting equals, it also impacts get hash code. Because get hash code also has use this method, can compare bits or use fast get hash code method, where if we take a peek at the code, okay, I'm not sure if I can read it, but if we take a peek at the comment, this unveils that if it can't use the fast, so if we have padding or a GC pointer, then, where is it? We look for the first non-static field and get its hash code. Let's give that a try. So if we have, let's comment out our benchmark. If we have, did I mess with our types? Are they still in the order? Yeah, let's remove all of that to have the original. Oh yeah, Control Z.
Oops.
So we have one, which is, maybe let's call this a padding struct.
Nice.
And a tightly packed struct. And if we now, and we actually have 3 values. So perhaps we should also add a constructor to be able to set these. Well, we could make them public, but yeah, let's not be. Do we want to do some more shenanigans, making fields public?
Yeah.
It definitely is well, this could also go into pure evilness. Not good, shenanigan. Field shouldn't be public now, because this is leaking now implementation detail, and it's difficult to impossible to change this type ever. If we had a property, we could still implement this property differently, but not revealing implementation details. Now we can get our tightly packed struct. And let's set value 1 to 1, value 2 to 2, and value 3 to 3. And we would expect that if we had a T1 and a T2, and the T2 now wouldn't have 1 to 3, but 1 to 4, well, we would expect them to have different hash codes. So let's do a write line on T1.get hash code and T2.get hash code. And well, we would expect 2 different hash codes. And indeed.
Yay.
But what if we check to the padding struct?
Uh-oh.
Well, the comment said that only the first field is considered.
And that's
so
equal.
Only the one which is equal. So they now would return the same hash code.
Yep.
And they do indeed.
And they do indeed, even though they're not equal. Whoops.
Can you tell us an area where this could cause maybe not correctness problems, but performance problems?
Well, my head is going to dictionaries, right? Because they, if I remember correctly, they implemented with like little buckets, right? And they actually check the hash code, and then also the actual value if you actually find more than one object with the same hash code. So it will still find what you were looking for, but it will just take a little bit longer, and that could potentially, if you have a lot of structs with the same hash code, it could potentially impact your performance.
Tightly. Did I write this correctly? Tightly. Let's put this to the test. So let's say we create a new dictionary. We don't have dictionary initializers just yet, but they may be coming in the future. So we still need to be a little bit old-fashioned. And let's say our new padding struct. Actually, now a constructor would be helpful. So let's do a constructor. I guess there's a refactoring for that. Initial fields from constructor. Please add. Yes. Oops. Yes. And here as well. Cool. And we say, let's say 1, 2, 3. And the value is 1. And let's do the same for the tightly packed one. And all we want to do now is to find that string in the dictionary. So we say padding get new. Let's use exactly that one. And well, actually, I guess we should cause some hash collisions. So let's add a 1, 2, 3 and a 1, 2, 4.
Yep.
And let's find the 1, 2, 4, which now has the value 2. Let's do it like so. And then let's do the same for the tightly packed one as well, and see if we indeed get a performance difference there again. Hello, Laszlo. Thank you very much for joining. And Jason is mentioning equality should not equated with hash code equality. A string and a custom type should have the same hash code, but they're not equal. Could, yes, yeah. So, okay. Yeah, so we must not mistake hash code with equality. It's an well, two different instances may have the same hash code, although they're not equal, which is now causing a hash collision, which now may tank the performance of my hash collections, such as a dictionary. But yeah, the dictionary, the hash code doesn't have necessarily anything to do with equality directly. And let's see if indeed now where we have a key that has padding, where only the first field is used for the equality, we have hash collisions. And for the other, well, actually, maybe does this show, because we still, no, well, we didn't do, because, well, it's a bit, it's summing up multiple problems, because we get the verse get hash code implementation, which now causes hash collisions and therefore worse lookup performance. But we also have since with the equality we do the, how's it called? With equality we do the reflection. We also have bad performance there. So maybe we implement a creatable to show this, but leave get hash codes implementation unchanged. So I'm just commenting out the get hash code implementation so that the rest is fast and we don't have the additional boxing on the equals, and we really show the difference. We only show one thing because we are now currently showing 2 problems at once. And generating the equality members and commenting out the get hashcode implementation so that we do get the one that may only consider the first field. And yes, exactly. The boxing, we additionally had the boxing problem, because when the hashcode is not found, then we check by equality, and if we don't override the equatable, what we saw earlier, then we may also have boxing for the space equals implementation that takes just an object. And now we should only see the one problem, and
nice. That looks.
We see. Well, yeah, I guess. Well, okay, maybe performance isn't that bad, but we still have some additional allocation. Well, this could be because one struct is 8 bytes bigger.
Oh yeah.
Could be also related to that. It could not be that our dictionaries are too small so that it doesn't quite show. But yeah, if we had large dictionaries, then this would eventually show, because we would have a lot of hash collisions. If all of our keys have the same hash code, then we would do a lot of equality checks. So I guess then the shenanigan is to implement structs without implementing equality and letting it up to the base implementation of value type that just cannot be perfect because it doesn't know what code we are gonna write. And yeah, also as I mentioned earlier, if we would make it a record, then we just get all of that for free and we don't need to worry about it anymore.
I like that.
And yes, Lasso is also asking if it could be the layout of the struct fields. Yes, indeed. We covered that just a bit earlier, where we have a... Just briefly sum that up again. Removing all of that equality. Where we had a... Let's bring them onto one screen. Where we had... Oh, let's not make this a record. Where we had 2 structs. Both of them contain of 2 integers and 1 long, where we would expect both of them are 16 bytes. But the first one is actually 24 bytes. The second one is 16 bytes because of the layout, the sequential layout. We don't have any padding here, but we do get it here. And yeah, then have not only a bigger struct, but also a struct that has not the ideal implementations. Wonderful. What else could we shenaniganify to take a look at some implementations of .NET under the hood?
We've just had a bit of a look at dictionaries. And I remember you showing me some unexpected behavior in that context as well. Would you want to show me to that? Or
yes. Just before we do, if we do the auto, actually, let's confirm that. I never actually tried it. If we do struct layout auto on this one, no, they actually, let's do the sequential here explicitly, just to be super. So this would be now the padding struct now should no longer be a padding struct. How? And if we do have some compiler error, let's just get rid of this. Are they now indeed the same size? Size of... Oops. They should be. Well, this is what I would hope. Tightly packed, and let's give that a run. And yes, indeed, yeah. Now the auto is causing it to be realigned. But I do not know the rules of what now comes first. If this is now int long, or if it's long int.
Oh.
But yeah, and now it's tightly packed, and now we get the fast algorithms again. Yeah.
Nice. Perfect.
Cool. But what if we change our key to a reference type? Is this what you meant earlier? Do I remember correctly? Yep. We have a class, and let's say our key maybe consists of a integer value. And let's also build a constructor for that constructor. Oh, yes. Cool. Let's see that as well. And let's again have a benchmark. Let's do a public. Oh, wait a minute. No benchmark. Let's do a dictionary.
Yep.
Which takes our key and our value. Let's say we do a string as a value. And let's add a new key. Let's say a 1. Or let's say, 1. And the string 1. And a 2 and a 3 with the string 2 and 3. Oops, if I could write. Maybe let's for each over this dictionary, which returns us with key value pairs. And let's then print them where we see the key should be key and the value should be value. Yes, thank you very much. I would now introduce some variables for this. Key 1, 2, and 3. 1, 2, 3. Key 2, key 3. And for the grand finale, let's do some dash dash, and let's then get from our dictionary, let's index into our key 1. Let's see if we get what we expect. We would iterate through our keys and value pairs. We only get the type here. I guess what we want to do is to override the toString of our key type.
Yep.
toString to say key colon value, something that resembles how record would do it, because I kind of like that format.
Okay.
Oops. Yes, please. A second one. And let's see if this goes as we expect. Yes, so we have our keys and our values.
Yes.
But our key is mutable. You mentioned some shenanigans with throwing something away. What if we now say the value of this to be, let's say, 3?
Yeah.
How does our dictionary now look like?
Oops.
We now have the value 3 2 times in there.
So what do you now get when you ask for the value of key 3?
If we ask for key 1,
yeah. Well, we don't key 1.
In our type, we don't overload equality nor get hash code. So maybe let's do that. Equatable of our key. Generate equality members, and we get equality, and also they get hash code, which just returns the value. And it says no. Oh yes. Oh yeah. Here we get the writer gives a shenanigan. Perhaps yet another potential analyzer. Where get hash code includes something mutable, because now if we go in with key 1, this is no longer by reference, but now by value, because our type is now doing value equality. Now we no longer get the 1, but we actually get the 3.
Wow.
So we kind of no longer can access the 1.
We cannot access the value, yeah.
We kind of masked that key.
Okay.
Threw it away. Because we had a reference, because we have a reference type here, which is now mutable. We keep the reference to that key. We let the dictionary add this key into the dictionary, doing the get hash codes and all of that. But then we change that value.
Yep.
Which changes both the get hash code but also the value equality, and then have a scenario which actually shouldn't be possible if we were to do it immediately, if we were passing in the same key twice. We would actually get an argument exception here, because the same key has already been, or an equal key has already been added. But if we mutate it after the fact, then the dictionary doesn't know that something else still has a reference to it, and then starts pulling the rug under its feet, kind of a thing. So actually, why does gives the fun away of our shenanigans?
Yeah, a little bit.
Well, it usually is good, but for first April Fool's episode, it's bad. But perhaps we build in an analyzer project, and we call it the anti-shenanigan analyzers, so that we could include it also in the .NET build and not just in the wider IDE scenario.
Yeah. The shenanigan police.
Is this an idea for another talk or another episode?
Could be.
Browsing public repositories and uncovering shenanigans. Sweet. Do we have one more shenanigan on our list?
We do.
Ooh. What do you want to do next?
I want to talk about memory pools and what could happen there. Does that make sense?
Yes. So what's memory pool? Let's start with an array pool. Array pool is a type to, actually every pool is a performance optimization so that we reuse heap allocated objects. So if we need to allocate and deallocate on the heap very often, we could do it only once or less times and then reuse these objects.
Yes.
But what if we don't properly give it back? So let's say we have, there is a shared array pool. One could also create their own array pool. But if you want to be application-wide, share, have the same shared pool, you can use that. And with the pool, we could rent a new array. Maybe let's say we need at least, the thing is, this is minimum length. Because array pool doesn't pool every length of arrays, this would kind of allocate a lot different arrays again. I'm not sure exactly what the rules are, but there are some rules in place. It ensures that we get at least this minimum length, but not above that length. Actually, a nice usage pattern could be if we well, when we rent an array, now we have an int array here. We rent it from the pool. So it's now gone from the pool. Nobody else could rent that same array. That's now ours. We have ownership over it. Well, which also means that eventually we should give it back. We should be good. What we borrowed, we should give it back. And additionally, we could say, should these elements be cleared? So in our case, our integers all set to default so that all the values are back to 0. Maybe if we store some sensitive data, like passwords or something like that, we may want to return it back so that no other application to do something, no part of the application could do shenanigans with it.
Okay.
And well,
so
actually,
you rent and return. Mm-hmm.
We rent and return. Yeah, that's the pattern. I guess, I'm not sure. Maybe there could be an analyzer. I guess it's more difficult to detect, but this could also be an analyzer indicating, hey, if we don't return what we rented, well, it's not really, it would kind of then starve the pool, because if we always take back but never give back to it, then at some point the pool would need to allocate new arrays again, which defeats the purpose of this performance optimization.
Yeah. And I guess, is it quite rare for C# to have like something like that, where you sort of like have to take care of a resource, like delete it or like return it or do something like that? I guess I've never seen that. And do you know what I mean?
It usually happens in infrastructure code a lot. So it's rarely that you use it in your application code. But I'm not guessing, but I could imagine, I'm not entirely certain, but I could imagine that ASP.NET Core is using something like that under the hood. Well, I can imagine that if they need smaller arrays, they need smaller memory, smaller pieces of memory. They may allocate them on the stack, via stack alloc. But if there is, well, and really for any infrastructure code, messaging, if you get messages from a network stream and want to deserialize them, and they're maybe bigger, then I guess for such code, having these buffers reused could be a great performance optimization. But you rarely do it in your in high level application code.
I guess I'm just sort of saying this is like one of the shenanigans that would definitely kind of happen to me by accident, kind of like the first one, where I just rent it, I do my thing, I get lost in something else, forget to return it, death, or I reuse it after something like that.
Yes. Because actually we actually get length 16.
Yeah.
So that seems to be the minimum size that this array pool has. So you could build your own array pool. And yes, Lasso lets us know to put this into a try finally, because what if something goes bad, then we get an exception and maybe we never return to the pool. So we now made it safe. So if we do, before we return it, anything goes wrong before we return it, we now definitely return it.
Yeah, that makes sense.
That's a good addition. And then after we return it, we shouldn't really use anymore. So what we could, what you meant, what if we use it after returning? We could be it's changing 1 to a 99. And let's say this is now, maybe we leak this reference out, it kind of escapes, and now some other component in our code base is now holding on to it. So we say we both return it and yield ownership, but still either keep ownership or pass it off to somebody else. Now, if somebody else would now go ahead, let's say we are now in someone else would also want to get an array. Maybe they want to have a minimum size of 8 and would like to have this array initialized with maybe 0, 1, 2, 3, and so on. 4, 5, 7, yes.
I'll help. No, you're faster without me.
And let's for each over it. Oops, for each. All the values. But yeah, somebody in between.
Me.
Someone. You. Still having ownership to which was returned. This could be, well, this could be in a totally different thread or something. And now, well, I set it to, wait a second. Oh, yes. Oh, sorry. Well, our actual length is not 8, but our actual length is 16. Well, we request 8, but we actually get 16.
Generous.
But although we set an index 1 to 1, somebody else could still set it to 2. Which, well, I guess it's generally a problem when it comes to ownership with shared mutable resources. The ownership must be clear, and only one. If it's like a pulled object, don't use after. First of all, properly return, because this would otherwise break the, well, not break, but mitigate.
Yeah.
Nullify the performance benefit of the shared array, of the shared pool, but also use after returning. This also could be a nice analyzer that we still have in the reference here. Here it's returned. It shouldn't be used here anymore.
Shouldn't be used here. Should get some. Yeah, because this could be quite dangerous, I guess, if you're working with people who don't know what they're doing, or if you're just missing it, like me.
Yep.
But so what? What is then? Because so it seems to be like in this context, obviously we're playing around with it, that it's actually quite risky to use like an array pool. But is it that much better, or like against what is the big benefit, like the performance again, or
the performance? Yeah, because if we would always allocate a new array of size 4, or maybe in our case we always need 100 integers.
Yeah,
maybe 100 bytes, something that is, well, maybe something larger that we can't really allocate on the stack. Or if we are in an async scenarios, then we may also have trouble using, because using span, maybe we come to that. There is a usage pattern that works very, very nicely with arrays, but in some scenarios we can't then use it anymore. And I totally forgot my trail of thought. But yeah, so if we don't want to, either if we can't stack allocate because of async scenarios, or if it's bigger chunks of memory that we continuously allocate, then keeping a shared pool around and reusing that can be a significant performance improvement. So I guess in general, whenever you see something with pooling, that is performance optimization.
Nice.
Okay. But also a potential problem.
Yeah, when used incorrectly. Yeah,
use cool. After, I guess in well, the comparison is not ideal, but if we were in C++ land, and if we would use something after we delete, if we had a pointer to something and we deleted that resource, we use after delete. Well, this is very, very bad. This is use after return, or after yielding ownership of this managed resource. It's not memory unsafe, but we could cause undefined behavior, unexpected. Well, maybe it is kind of defined. Depends on what we're doing, but at least unexpected behavior.
Fair enough.
And maybe when we come to the end of it, maybe let's stop doing shenanigans. Maybe let's do something good for a change.
No way. Yeah, let's. Why not?
Let's go into anti-shenanigan mode. Because, well, what we see here is that we are requesting an array with at least minimum size of 4, but we actually get one of size 16. So we need to additionally then keep our ideal length around. So maybe if we then for each it, or actually for it, and say array index I. Well, in this case, we would now print, well, it's initialized, so we will get 16 zeros, but we would need to keep this length around somewhere. Well, maybe we store it in a length variable here, and then have something like this. But we still now have kind of two disjoint variables. And this is where the array segment comes in. You could create, now actually we haven't prepared for this, so this is kind of ad hoc, so I may do some mistakes here. Array segment. An array segment, we mentioned earlier that the span is a view into contiguous memory.
Yep.
The array segment is more or less the same, but only for arrays. And it existed way before. I'm actually not sure since when does array segment exist. Let's go to APIs of .NET. Well, it is a generic type, so I guess that's at least .NET 2 or something. Array segment of T, this works like that. System array segment. So this exists since, yeah, .NET 2. So that's an old type. Span is well, it's not that young anymore, but a younger type. We could create a new array segment where we pass in, I think, the array and the expected length, if I recall correctly. We could also do an offset. So how we get the slicing. So we could also kind of have a similar semantic. So we could say, let's pass in the array with an offset of 0, because we start at 0, and then pass in the length. And now if we use the segment, we now have this limited view over the array. Well, the array segment still has the original array, but its indexer and its for each, or its get enumerator and all of these, they respect the offset and the count of elements. So if we now, and now this basically groups our array and its length together. So we could say segment.length, or sorry, segment.count. Or I think we could also now turn this into a for each loop. Because, well, array segment implements get enumerator in a fashion that respects the start, the end, and so on. And we now put those two together in a singular type. And yeah, we can now for each it, we don't need to worry about this length. Well, under the hood, it's still this 16 length array, but we just get a view of 2 into it. But this array segment only works for arrays. Okay. And span is the more modern version of it, because span not only works for arrays, it also works for native memory or for stack allocated memory. Actually, what we could, so we could now create a new span. We could just create a span of int, our span. And then, well, this span now still, because we just have some, we can implicitly cast an array into a span, but now the span is still the full, well, the actual 16 length array that we get. So if we would say span here, oh, actually, yeah, we should keep the original array so that we can return it at the end. And we just say array goes to span. But the span now represents the full 16 length array. But we could now do what we had earlier, the slicing. Sorry, let's cast it to a span. We can also do it explicitly as a span, and then slice into it. For example, let's start at 0 and use our length of 4. And that's functional, not the same thing as with the array segment that we had. Technically under the hood, it works a bit differently because the span doesn't have a reference to the entire array, but only to the beginning, or to some, not necessarily to the beginning, but to some element within that array. And we could now narrow the view by slicing. Maybe we only want to get, if we have an array, let's say index 1 becomes, index 0 becomes 1, index 1 becomes 2, index 2 becomes 3, and index 4 becomes 4. Sorry, index 3 becomes 4. We could say, okay, I only want to have a view into the second and the third element. So we could slice after 1, and then with a length of 2. And now our span has only a length of 2, and only the 2 and the 3. And this is the power of slicing, because we don't allocate any new array. Well, with array segment, we can do the same thing. But with span, we don't allocate anything new. We just narrow the view.
Nice.
And the cool thing is we could also do this with stack allocated memory, because you can just create a span of int. And yeah, already tells me to stack allocate. Well, I would also call it length. Span 1. We need to be careful. Do you know what would happen? Let's say these are bytes. Let's create a byte, and we are on Windows, and we would allocate. So that's a kilobyte, a megabyte, and maybe let's allocate 10 megabytes of memory. Do you know what's going to happen?
No.
If we allocate too much space on the stack?
Stack overflow?
Yes.
No. Really?
Yep.
We can cause it. Oh my goodness. I always only know it from like these infinite loops and stuff. I've never actually just created one like that. Nice.
It could cause by infinite loops, because every time if you cause a method indefinitely, you will always create a new stack frame, which will always allocate new memory on the stack.
Yeah.
There is no infinity on the stack, but you can also just with one go just allocate too much space on the stack. I think the recommendation is never to allocate more than a kilobyte. I'm not sure if this is a kilo or a KB, so maybe like so. But if we need larger chunks, then the array pool would be our way to go, to still be, well, not necessarily allocation free, because at some point we still need to allocate that array, but eventually then when we use these arrays multiple times, then is that amortized allocation freeness? I'm not sure if I'm using the right terms here. Using fancy terms.
Fancy terms. Sounds fancy. I believe you.
And then also returning it. Actually, this pattern is very common. That there, I hope I'm using this now correctly. There is also now a memory pool.
Yep.
Where we can also just need to take a brief peek. Okay, so this parameter is called differently, where we can also rent minimum size.
There's no maximum, is there? With this?
No, because we don't really want an array of variable length. If you want to have an array of variable length, then you create a list. Because and then if I need a specific size, then I request that minimum size that I need.
Fair enough.
Does the other? Yeah, I'm not sure if the other has give me something between this and that. What if that wouldn't be fulfilled? Then what would happen? Would it say no, not such an array available?
No.
I'm not sure if there's
Ask someone else.
But this now doesn't return memory. It returns a memory owner. And the cool thing about memory owner is it's disposable. And I think under the hood then takes care of the returning it. If we would take a look at the implementation, I think under the hood, what this memory pool is, it's this array memory pool. And we create an array memory pool buffer. And this array memory pool, can we go to the type? Okay, I'm not sure where this type lives. We need to jump to source.net, but I'm always just finding excuses to go to source.net. And yeah, now this implements iMemory owner, and it's disposed. So in its construction under the hood is an implementation detail that just uses the array pool.
Oh.
And in the dispose, then returns it. So we kind of get this pattern encapsulated, can then do a using, and then don't need the finally and that. And since this is a memory this is a memory owner, and the memory owner has memory, and with the memory we can get the span. And I think that does the memory owner, now I'm not sure, if we request, let's say 4, does the memory owner already only know the 4 bytes? So if we were to check the length of this memory, would this be 4 or 16? Oh, it would be 16. Okay, so we would actually get the actual length. So again, we would need to, would we need to do the slicing again? I suppose so, to get our actual size that we need. Laszlo is letting us know when creating a custom pool. Then, or when we create, so when we create a new inst, because we can actually new array pool. I never did this array pool. Is there, maybe it's a create array pool. Is there a .create method? .create, yes. We could have a max array length and the max arrays per bucket. Okay, I'm quite unfamiliar with the implementation of array pool. But yeah, I guess the documentation would reveal it of how to use this correctly. If we're not happy with the default shared implementation and we want our own array pool that is also not shared with anybody else. So we could now basically, nobody else gets arrays out of my array pool. Yes.
Exactly. All right. Well, but that wasn't, we're kind of out of shenanigan land. That's actually how you would normally use it and create expected behavior, right? Do we have any more shenanigans?
Taking a look at the list. No, well, we do have a bit of a stretch goal if we want to jump into that.
What's the stretch goal?
To see the drawbacks of a span in.
Yeah, let's have a look at span.
Because although span is super, super powerful when it comes to non-allocating scenarios, or an abstraction over arbitrary memory, because it can be my arrays, it can be my stack allocated memory, some native memory. It does have its limitations. Stu is asking, is there something about there being a perf benefit in using the default pool, because it will use a thread local instance first, whereas custom pools don't have this behavior? Oh, sorry, not a question, but an indicator. Yeah, I was quite unfamiliar with the implementation. So using the default pool is better than using a shared, using the shared pool.
Oh, nice.
Yields a perf benefit because okay, so this is not just a this is not just a regular array pool that is created. It's actually a separate type, a shared array pool that okay, I'm not conditional weak tables. Okay, I couldn't explain this type. I never used it. But this looks like this looks mega high perf. That's a Stephen Thorpe tip. The shared array pool is quicker than a custom pool. Span. Span has a bit of a limitation. What if we had let's create a public static class to make it more obvious. Class with a public static async task method. We can't pass a span to it. Well, let's make it non-generic. In async methods, we can't pass a span.
Yep.
Because a span is a ref struct, and the ref struct can only be on the stack.
Yep.
So we have our classes that usually are always on the heap, which may with future versions of .NET be so true anymore, what we also discussed in product memory management episode, because the runtime will now smaller arrays that are of primitive types and are not big and don't contain GC pointers could be, if they don't leak out, if they don't escape out of a method scope, then they may be stack allocated. But so the runtime also does more optimizations. But so I guess I now need to say a class usually is on the heap.
Yep.
A regular struct may be on the heap unless we box it.
Yes.
A struct may be on the stack unless we box it onto the heap. But we also saw with the casting it to object or casting it to the interface it implements. But a ref struct can only be on the stack.
Mm-hmm.
And since when we have an async method, well, we actually get the state machine. If we were to...
There's that word again.
If we take a look at this method now, it kind of... Well, this method now looks different. Our method... Well, I should have added some code. Well, this method is empty, but it's not empty anymore. If I would have added some code, this code wouldn't be there, because what actually gets generated is the state machine that now has this parameter to this method actually as a field. And this state machine is a class. If we compile it in release mode, I think then the state machine is a struct. But since classes and structs may be on the heap, it can't contain ref structs, because if we have a ref struct as a field, this could now escape to the heap, and that's not possible. There are some memory, because what if this span is representing some stack allocated space, and we would let this stack allocated space escape to the heap, then the ownership isn't clear anymore, and then stuff gets very shenanigan-y again. So that's one limitation. Well, we can't also. Well, the reason with Stuart has showed us this in the C# 13 tip. Previously, we couldn't have spans as locals either. So if we were writing this code, and maybe let's then have our console write line with something, or let's actually make this an async method. Let's do an await task.delay for 10 milliseconds. Now, in earlier versions of C#, this wasn't possible because not only parameters, but also local variables could become could become fields in the state machine.
Mm-hmm.
But span is a ref struct. It can't be a field a ref struct can only be a field in a non-ref struct. Excuse me, I'm saying it wrong. A ref struct can only be contained in another ref struct, but not in a class or reference, in a class or struct. But it's actually possible now, unless, maybe let's slice into it. This wasn't possible earlier, now it is possible, but still it can't be across await boundaries. Okay. Because now it would need to become a field. Because the state machine, well, especially if we delay here, our state machine would return later on. When this task is completed, we would resume our state machine and then continuing there, which means how do we remember the state from here to there of a method that is called multiple times? It needs to be a field in the state machine, and this is not possible. But if it is within boundaries, it doesn't need to be a field. It can be a local, and then we still have those ref safety rules fulfilled. And the same phenomenon is also in iterator methods. If we were to change this in iNumber of int, and if we were to start yielding, let's say this returns 1, 2, and 3. And what am I doing wrong? Oh, IEnumerable. Then again, this will be turned in a state machine, not in an async state machine, but in this enumerable state machine, which is very nicely consumable in a for each loop. But again, we have the same problem. We can use it within yield boundaries, but we cannot use it across yield boundaries because it would again become a field in a non-ref struct, which is not possible. And yeah, so although span has its limitation, it also yields a lot of power. Good power, but also, well, you could do, in general, when you have a ref or a pointer, you could do some memory-based shenanigans.
Yeah, what's the saying? With great power comes great responsibility.
Yes, indeed.
So I didn't quite catch what, like, if the span slice thingy is before the yield, what does this then look like under the hood? You said it's going to be like a local.
Yes. So we will now, if we compile this.
Yep.
Well, actually, really any usages of a span, I'm just slicing into it just to have some code, really any usages. I mean, we could just have something simple as just doing something like this here. Yep. Just to a discard, we're using it across await or yield boundaries. It's not possible. If it is within yield boundaries, maybe that's actually, maybe we should do something with it so that the compiler doesn't optimize it away. Or become a 1. If used within the await or yield boundaries, it will not become a field. So what we will see, maybe let's pass in integer length here that we use there. We will see this become a field, but we won't see the span. We will also see this owner become a field because we have a using here. So at the end of the state machine, this needs to be in a finally block disposed. We see these all become fields in the state machine, but the span will not. And let's see if this holds up. So we have, where's our original method? This is our original method. This now changes into, we create here a new instance of the state machine. We set some state of this state machine. And the move next, which is called every time we call into the for each loop. We now see that taking a peek at this object, we have the length parameter is a field. We have this memory owner became a field, but the span did not, because the span cannot. So we will see the span here being used, but not as a field of this state machine type. Unlike, for example, the owner, this memory owner, because the memory owner eventually needs to be disposed in a finally block. And I guess, there is a lot of stuff going on in the state machine. And there it is. Here's the dispose. And so all the locals and arguments may become fields in a state machine, and web structs cannot.
Okay, fair enough. Fair enough.
Or better to say, they must not, because then we could start breaking our expectations of how long stack allocated space is living. And I believe Shahab is kind of initiating the end. I'm afraid. Very much afraid.
I'm afraid so, but it was a really cool. I had fun because we had an episode full of shenanigans, an April Fool's episode where we created some unexpected behavior and sort of looked under the hood at what was happening and how this could occur. And I really like those things because it looks like magic. It makes me really happy. In this setting, at work, it would make me very unhappy. But
yes, indeed.
On days like this, you have to take it with a bit of, fun spirits. Thank you so much for joining, Laszlo. Have a great evening. And also thank you to everyone else who's been here with us. It's been really a pleasure to have so many familiar faces here today as well. If you haven't already, please make sure you subscribe to any of our social media channels, because as we said at the beginning of the episode, we're going to take a bit of a break of the stream, just because we need the time to prepare our wonderful conference talks. So if you happen to be at the NDC Oslo or Techorama in Belgium, stop by, say hello. We're going to be there, and I'm going to be so excited. I'm going to be jumping up and down for the whole 3 days of the conference. But yeah, that means that we have to take a little bit of time off the stream. Only a couple of weeks. It's not going to be too much of a break, but because we do not yet have a set date for our next episode, make sure you subscribe to our social media so you do not miss it when we announce it. And I think it's going to be a great episode. Potentially, we're going to tease it again, but it might actually be time for a benchmarking episode. We'll see. Will be very good. Have you finished the book already, actually?
No, I haven't.
Okay, so you'll have finished it. You will have finished it.
I might.
When we come back.
I might.
Thank you so much, Stuart. I'm going to need all of the luck, especially because with the code, like with the live coding. But I think it's going to be awesome.
But don't worry, I need all of the luck too. Because we're going to do, we're not only going to do shenanigans, so even more of what we did today, we also will take a peek at how language patterns work under the hood. For example, we had a for each in our episode, or an async and await. Can we use this with any type? Well, the answer is yes, and we're going to show how.
Spoiler.
Toasting Training is wondering if these talks will be live streamed or recorded. I'm not well, I don't think they are being live streamed. The NDC talks usually get published on their YouTube channel a little bit later, after the conference. And I think the Techorama ones, you can get them if you have a ticket. They are, I think, then in for attendees to watch again, or for episodes, or for talks that they have missed because of the multiple tracks, I believe. Oh, that's so kind of you.
Thank you.
And perhaps the closing quote of the day: "Luck is a flavor for prepared mind, and no one is as prepared as you two." Well.
No, yeah, absolutely right. We're gonna be super prepared, especially starting quite early. But I also think Toast Training is correct. It's going to be entertaining one way or another. Either it's going to be entertaining because we're very well prepared and everything's going to go well, or it's going to be hilarious because I take 5 minutes to code one line. Could be.
Wonderful. Thank you very much for joining this episode. It will be a while, but unquestionably we'll be back.